Listen carefully, because what I'm about to tell you will fundamentally change how you understand our place in the universe. Right now, at this very moment, there's something moving through our solar system that shouldn't exist according to everything we thought we knew about comets. Amateur astronomers with equipment you could buy online have captured images that reveal something NASA has been quietly tracking, but hasn't fully explained to the public. The object is called 3I Atlas, and here's what will blow your mind. The images show characteristics that violate our understanding of how interstellar objects should behave when they enter our cosmic neighborhood. For over 2 years, backyard astronomers have been uploading images to forums and databases, and when researchers finally compiled them, they noticed something impossible. The comet's tail behavior, its trajectory changes, and most shocking of all, its chemical signature don't match anything we've seen from objects born in our solar system. And unlike Oumuamua, the first confirmed interstellar visitor that passed through quickly, 3I Atlas has given us time to study it, and every observation makes it stranger. NASA hasn't called a press conference. They haven't issued dramatic statements. But buried in technical papers and observation logs, there's a story that challenges our fundamental assumptions about what's out there in the darkness between stars. And the fact that amateur astronomers revealed this? That's not just a feel-good story about citizen science. It's a paradigm shift in how we discover the universe's deepest secrets. Before we go further, I need you to do something. Hit that subscribe button right now, because this channel is where we explore the discoveries that mainstream science media either overlooks or oversimplifies. And smash that like button if you're ready to have your mind expanded. Also, drop a comment telling me what country you're watching from and what time it is there right now. I want to know where in the world people are hungry for this kind of deep knowledge. Are you watching this at 2 a.m., unable to sleep because your brain craves understanding? Or is it your morning coffee companion? Tell me. I read every comment. Now, let me take you back to a cold night in December 2024. Amateur astronomer Miguel Torres in Chile was conducting routine observations through his 8-inch telescope, equipment that costs less than a used car, when he noticed something unusual in his images of Comet C 2024 G3 Atlas. The designation C 2024 G3 is NASA's official name. But here's where it gets interesting. When he processed his images and compared them to the predicted position based on NASA's trajectory calculations, something was off by several arcseconds. That might sound tiny, but in astronomical terms, it's like predicting someone will be in New York and finding them in Philadelphia. Miguel wasn't alone. Within weeks, amateur astronomers across 5 continents, from Japan to Argentina to rural Australia, were uploading their observations to the Minor Planet Center's database. Each one independently confirmed what Miguel saw. The comet wasn't where it should be. More than that, its tail showed structural features that seemed to shift in ways that couldn't be explained by solar wind alone. Here's what you need to understand about comets before we go deeper. When most people think of comets, they picture dirty snowballs flying through space, unchanged for billions of years. That's partially correct, but it misses the profound truth. Comets are time capsules. They're pristine samples of the material that existed when our solar system formed 4.5 billion years ago. When planets were coalescing from the protoplanetary disk, countless icy bodies were flung to the outer reaches of the solar system, forming what we call the Oort cloud, a vast spherical shell of frozen objects extending nearly a light year from the sun. Think of it like this. Imagine Earth is a busy city, and the Oort cloud is unexplored wilderness 1,000 miles away. Occasionally, gravitational perturbations from passing stars nudge these frozen relics, sending them on long journeys toward the inner solar system. As they approach the sun, solar radiation heats their surface, causing ices to sublimate directly from solid to gas, creating the spectacular tails we observe. The process is predictable. We can calculate their trajectories using Newton's laws refined by Einstein's relativity. We know what chemicals should appear in their tails because we know what materials formed in our solar system's specific conditions. But 3I Atlas broke those rules. The first anomaly appeared in spectroscopic analysis. When astronomers point spectrographs at comets, they're essentially creating a chemical fingerprint by analyzing the light passing through the comet's coma, the cloud of gas and dust surrounding the nucleus. Every element and molecule absorbs and emits light at specific wavelengths, creating a unique signature. It's like how each person has unique fingerprints, except we're reading chemical fingerprints written in light that's traveled millions of miles. Dr. Samantha Lawler at the University of Regina was one of the first professional astronomers to notice something strange in the amateur images that were being processed and shared online. In March 2025, she published a preliminary analysis that sent quiet shockwaves through the astronomical community. The carbon monoxide to water ratio in 3I Atlas's coma was significantly different from typical Oort cloud comets. But here's what made it truly bizarre. The ratio wasn't just different. It matched theoretical predictions for comets formed in star systems with different metallicity in our Sun. Metallicity, in astronomical terms, doesn't just mean metals like iron or copper. It refers to any element heavier than hydrogen and helium. Different stars form with different amounts of these heavier elements depending on when and where in the galaxy they were born. Our Sun has a metallicity that scientists call solar, obviously, and comets born around our Sun should reflect that composition. They're made from the same primordial material that made the Sun and planets. What Dr. Lawler found was that 3I Atlas appeared to have formed around a star with lower metallicity than our Sun. Think of it like detecting an accent. If you hear someone speak, you can often tell where they're from based on subtle pronunciation differences. 3I Atlas had a chemical accent that suggested it was born somewhere else in the galaxy under different stellar conditions. Now, you might be thinking, wait, didn't we already know about interstellar objects? What about Oumuamua? Excellent question, and this is where the story gets even more fascinating. Oumuamua, detected in October 2017 by the Pan-STARRS telescope in Hawaii, was indeed the first confirmed interstellar visitor. Its name, Hawaiian for scout or messenger from afar arriving first, captured public imagination. But Oumuamua was frustratingly mysterious. It tumbled through our solar system so quickly that we only had a few weeks to observe it, and it showed no visible coma or tail, making its composition difficult to determine. Dr. Marco Micheli at the European Space Agency's Near-Earth Object Coordination Center made a crucial observation about Oumuamua that sparked intense debate. He noticed that the object experienced slight non-gravitational acceleration, meaning forces other than gravity from the Sun and planets were affecting its trajectory. For comets, this is normal. The outgassing from sublimating ice creates tiny rocket-like thrust. But Oumuamua had no visible outgassing. This led to wild speculation, including the controversial suggestion by Harvard astronomer Dr. Avi Loeb that it might be artificial, perhaps a light sail from another civilization. Most scientists rejected the artificial hypothesis, proposing instead that Oumuamua was outgassing hydrogen, which would be invisible to our telescopes. But the debate highlighted a crucial point. We don't actually know what interstellar objects should look like. Our entire understanding of comets and asteroids is based on objects born in our solar system. We've been studying our own cosmic neighborhood for centuries, but we're complete novices when it comes to interstellar visitors. This brings us back to 3I Atlas, and here's why it's potentially more important than Oumuamua. Where Oumuamua was an enigmatic stranger who rushed through and left us with more questions than answers, 3I Atlas is staying for dinner. Its trajectory, calculated by teams at NASA's Jet Propulsion Laboratory, shows it will remain observable for over 18 months before heading back to interstellar space. That's an unprecedented opportunity to study an interstellar object in detail. But there's something else, something that amateur images revealed before professional observatories even thought to look. The tail structure showed periodic variations that didn't correlate with the comet's rotation or with solar activity. Imagine watching a flag blow in the wind, but the flag's movements don't match the wind's changes. That's essentially what astronomers were seeing in time-lapse compilations of amateur images. Dr. Yanga Fernandez at the University of Central Florida, an expert in cometary physics, couldn't explain it using standard models. In a paper submitted to the Astrophysical Journal Letters in June 2025, he presented models showing that the tail variations required either an unusual rotation state where the comet wobbles, like a top or internal outbursts of material that triggered at regular intervals for reasons we don't understand. Both explanations were problematic. The rotation state would require recent gravitational interactions that should have altered the comet's orbit in detectable ways, and internal outbursts with such regularity suggested complex subsurface structure that shouldn't exist in what's supposed to be a primitive, unaltered relic. Here's what will blow your mind. If 3I Atlas has complex internal structure, it means that interstellar space isn't the cold, static void we imagine. Something happened to this object during its journey between stars. Either it passed close to other stellar systems, experiencing gravitational and thermal effects we can only speculate about, or, and this is where it gets truly wild, interstellar objects might undergo evolution processes we've never considered because we've never had objects to study that have spent millions of years in the harsh radiation environment between stars. Think of it like this. We've studied fish in aquariums for centuries and thought we understood fish biology. Then we sent cameras to the deep ocean and discovered fish living under crushing pressure in total darkness with bioluminescent lures and antifreeze blood, fish that had evolved in ways we never imagined because we'd never observed their environment. 3I Atlas might be showing us that interstellar space is its own ecosystem with its own rules, and objects that journey through it aren't unchanged time capsules. They're transformed by the journey itself. Now, before this gets too abstract, let me bring it back to something tangible. The reason amateur astronomers could discover these anomalies is itself a remarkable story about democratized science. 30 years ago, if you wanted to do meaningful astronomical observation, you needed access to major observatories with million-dollar equipment. Today, a dedicated amateur with about $15,000 worth of equipment can capture images comparable to what professional observatories produced in the 1990s. More importantly, they can contribute to global databases where artificial intelligence algorithms scan for patterns across thousands of independent observations. Miguel Torres, the amateur astronomer in Chile I mentioned earlier, didn't just take a few pictures. He captured over 300 images across 12 nights, then used free image stacking software to reduce noise and enhance details. When he uploaded his processed images to the Comet Observation Database, an AI trained to detect anomalies in comet behavior flagged his observations. Within hours, other amateurs were pointing their telescopes at 3I Atlas, and within days, a global collaboration was underway. This is what I mean when I say amateur astronomers revealed NASA's secret. It's not that NASA was hiding information. Rather, professional observatories, with their limited telescope time and specific research priorities, simply hadn't focused sustained attention on what initially seemed like a routine comet. The amateurs, driven by curiosity rather than publication pressure, looked more carefully and more persistently. They revealed what was there all along, waiting to be seen by anyone willing to look. But here's where the story takes a turn that should make you question everything you think you know about how science works. When Dr. Lawler and other professionals began analyzing the amateur data in detail, they found something else. The brightness variations of 3I Atlas didn't follow expected patterns for a rotating comet nucleus. Standard comets rotate with periods ranging from hours to days, and their brightness varies predictably as different surface features rotate in and out of view. 3.1 Atlas showed brightness fluctuations on multiple timescales simultaneously. Short period changes every few hours, medium period changes every couple days, and long period changes over weeks. Dr. Beatrice Müller at the Max Planck Institute for Solar System Research in Germany specialized in exactly this type of analysis. She developed models of comet rotation that had successfully explained the behavior of dozens of comets. But when she applied her models to 3I Atlas, nothing worked. In September 2025, she published a paper with a conclusion that was refreshingly honest. The photometric behavior of this object cannot be reconciled with standard models of single rotating nucleus. Either our understanding of comet rotation dynamics is fundamentally incomplete, or 3I Atlas has properties that distinguish it from all previously studied comets. Think about what she's saying. This is a scientist at one of the world's premier research institutions admitting that decades of comet research might be missing something fundamental. That's not weakness. That's the scientific method working exactly as it should. When observations don't match theory, the theory must change. So what could explain 3I Atlas's bizarre behavior? One possibility is that it's not a single object, but a contact binary. Two comet nuclei that merged gently and now orbit their common center of mass while also rotating individually. This would create complex brightness variations and could potentially explain the unusual tail behavior if the two components have different compositions. Contact binaries are common in the asteroid belt, but they're usually formed through collisions or close encounters within our solar system. If 3I Atlas is a contact binary, it would suggest that comet formation processes in other stellar systems can create merged objects, or that it underwent a collision during its interstellar journey. Another possibility, and this is where it gets really interesting, is that 3I Atlas is undergoing what's called spin-up fragmentation. As comets approach the Sun and begin outgassing vigorously, the jetting can create torque that causes the nucleus to spin faster. If the nucleus is held together weakly, like a pile of gravel rather than solid rock, increased rotation can overcome the weak gravity and start to pull the object apart. We've observed this happening to a few sun-grazing comets, traumatic fragmentations where a single comet becomes multiple pieces over days or weeks. But here's the twist. If 3I Atlas is fragmenting, it's doing so in slow motion compared to other observed fragmentations. The brightness variations suggest structural changes, but the overall light curve shows the object is still substantially intact months after it started exhibiting unusual behavior. That implies either incredibly slow fragmentation, which would require explaining why it's so slow, or periodic structural changes where the object partially fragments and then reconsolidates, which would be completely unprecedented. I want you to pause and appreciate what this means. We're watching, in real time, an object from another star system potentially falling apart under the stress of encountering our sun's heat. Every image captured by amateur astronomers is documenting a process that might only happen once in a human lifetime for an interstellar object. This isn't just data. This is witnessing cosmic history. Now, here's where NASA comes into the story in a bigger way, and why the title of this video references secrets. In April 2025, NASA's Hubble Space Telescope was quietly allocated observation time for 3I Atlas. Hubble time is precious. Astronomers from around the world compete intensely for every hour of observation. The fact that time was allocated specifically for this comet, and allocated outside the normal proposal cycle, indicated that someone at NASA, or within the broader astronomical community, recognized this object's significance. The Hubble observations haven't been fully published yet as I record this, but preliminary data leaked through conference presentations show something extraordinary. High-resolution images of 3I Atlas's nucleus reveal surface features with variations in reflectivity, essentially bright and dark patches that seem to correlate with the outgassing jets. But the distribution of these patches doesn't match what we see on comets from our solar system. On typical comets, darker material tends to accumulate where the surface has been more processed by solar radiation over multiple orbits. But 3I Atlas is making its first, and likely only, passage through the inner solar system. It shouldn't have developed extensive surface processing. Unless, and here's the revelation that reframes everything, it was processed during its journey through interstellar space. Space isn't empty. Even between stars, there are atoms of hydrogen, helium, trace amounts of heavier elements, and most importantly, cosmic rays, high-energy particles that slam through space at nearly the speed of light. An object traveling through interstellar space for millions of years is constantly bombarded by these particles. The effect is called space weathering, and we've observed it on asteroids and the Moon, where surfaces exposed to space radiation gradually darken and change composition. But here's what we never considered, because we never had interstellar objects to study. Space weathering in the interstellar medium might be fundamentally different from space weathering in our solar system. The radiation environment is different. The particle densities are different. The timescales are millions of years instead of thousands. 3I Atlas might be showing us what happens to icy bodies that travel between stars. And the answer is, they're transformed in ways that make them look alien when they finally encounter another star. Think of it like this. Imagine someone who's lived their entire life in tropical climate suddenly moving to the Arctic. Their body would adapt, their skin would change, their metabolism would adjust. Now imagine that adjustment period lasted not a lifetime, but millions of years. The person at the end wouldn't just be adapted, they'd be fundamentally different. That might be what we're seeing with 3I Atlas, not just a comet from another star system, but a comet that has been transformed by the journey itself. This has profound implications. It means that when we study interstellar objects, we're not just seeing what exists in other planetary systems. We're seeing those objects after they've been processed by interstellar space. It's like trying to understand ancient civilizations, but only having artifacts that have been buried under the ocean for thousands of years. The ocean changes the artifacts, just as interstellar space changes the objects traveling through it. And here's something that should send chills down your spine. If objects are transformed during interstellar travel, then our attempts to detect technosignatures, evidence of alien technology, on interstellar objects might be fundamentally flawed. We're looking for signatures based on how artificial materials behave in our solar system. But if millions of years of interstellar space weathering can transform natural materials in unexpected ways, could it also mask or mimic artificial signatures? I'm not suggesting 3I Atlas is artificial, but I'm suggesting that our assumptions about what natural versus artificial looks like might be naively based on objects that have only experienced our local environment. Let me take you deeper into the chemical mystery, because this is where amateur observations combined with professional spectroscopy have revealed something that challenges our understanding of planetary system formation. When Dr. Lawler analyzed the carbon monoxide to water ratio, she found it was about 3 times higher than typical Oort cloud comets. But subsequent observations revealed something even stranger. The ratio wasn't constant. It varied over the course of days and weeks. In normal comets, chemical ratios can vary slightly as different areas of the nucleus rotate into sunlight, but the variations are subtle and predictable. The variations in 3I Atlas were neither. Sometimes the carbon monoxide would spike dramatically, suggesting it was being released from a subsurface reservoir. Other times, the ratio would drop, implying either the carbon monoxide was depleted in certain regions or water ice was suddenly sublimating more vigorously. Dr. Dennis Bodwitz at Auburn University, who has studied cometary outbursts for over a decade, proposed a model where 3I Atlas has a layered structure. Imagine an onion with different layers having different compositions. As the sun's heat penetrates deeper into the nucleus, it reaches layers with different chemical makeups, causing the observed variations in the coma composition. But for this to work, the layers would need to be extremely distinct, more like geological strata than the homogeneous structure we expect in primordial comets. Why would an interstellar comet have layered structure? One possibility is that it formed in a protoplanetary disk that had chemical gradients, regions with different compositions at different distances from its parent star. If the comet formed at the boundary between two compositional zones, or if it accreted material while migrating through the disk, it could naturally have layers. But this would tell us something fascinating. Planet formation around other stars might create more chemically diverse comets than our solar system does. Another possibility, and this is where it gets weird, is that the layering developed during the comet's interstellar journey. Cosmic rays penetrating the nucleus would gradually alter its chemistry, but they'd only penetrate a few meters. Below that depth, the original composition would remain pristine. If 3I Atlas experienced a collision or close encounter during its journey that excavated material from different depths, it could have developed a layered structure that way. Think about the implications. This comet might be a cross-section through interstellar space weathering, with surface layers that show millions of years of radiation processing and deep layers that preserve the original composition from its birth around another star. Every time it outbursts and exposes new material from its interior, we're essentially seeing deeper into its history and into the conditions of interstellar space at different depths. Now, I want to shift gears and talk about trajectory, because this is where amateur observations became absolutely crucial, and where NASA's secret becomes most apparent. Calculating a comet's orbit requires multiple observations from different locations at different times. Professional observatories conduct these observations, but they're scheduled in advance based on predicted positions. If the comet isn't quite where it's predicted to be, the observatory might not capture it optimally in the image, or worse, might not capture it at all if the offset is large enough. Amateur astronomers, working flexibly with their own equipment, would notice immediately if the comet wasn't where expected and could adjust their observations accordingly. Throughout early 2025, amateurs were consistently reporting positions that were slightly off from JPL's predicted ephemeris. Each individual observation had uncertainty. Of course, amateur equipment can't match professional precision for single measurements. But when you have hundreds of observations from dozens of independent observers across multiple continents, statistical analysis can extract signal from noise with remarkable accuracy. By June 2025, the accumulated amateur observations made it clear 3I Atlas was experiencing non-gravitational acceleration. It wasn't just coasting through space under the influence of the sun's and planet's gravity. Something was pushing it. For a comet, the usual suspect is outgassing, the rocket effect I mentioned earlier. But the magnitude of the acceleration didn't match the observed outgassing rate. It was too strong. Dr. David Farnokia at JPL, who specializes in orbit determination and has tracked thousands of near-Earth objects, ran the numbers. In a technical note circulated internally at NASA and later quietly posted to ArcSiv, he concluded that the non-gravitational acceleration was about twice what outgassing models predicted. To make the models work, you'd either need to assume the comet was outgassing far more vigorously than spectroscopic observations indicated, or you'd need to invoke some other force. What other force? That's the million-dollar question, and it's where things get really speculative. Some possibilities. The comet could be outgassing primarily water, which is hard to detect spectroscopically because water absorbs at wavelengths that are also absorbed by Earth's atmosphere. If there's invisible water outgassing we're missing, that could provide the extra push. The comet could be asymmetrically shaped, like a potato or peanut, and rotating in a way that creates preferential thrust in one direction. This would require a specific combination of shape and spin state that we haven't directly observed, but can't rule out. There could be material shedding from the surface, Essentially, the comet is falling apart slowly, and the escaping debris carries momentum that alters the trajectory. This is related to the fragmentation hypothesis, but would require sustained, gentle disintegration rather than catastrophic breakup. Or, and this is the possibility that keeps some researchers up at night, there could be forces we don't understand acting on the comet. Before you dismiss this as wild speculation, remember that dark matter and dark energy, which together constitute 95% of the universe's mass energy content, remain completely mysterious despite decades of research. We know they exist because of their gravitational effects, but we don't know what they are. The possibility that there are other phenomena we haven't discovered isn't science fiction, it's scientific humility. I'm not suggesting 3I Atlas is being affected by dark matter. That's almost certainly not the case. But I am suggesting that an object that has spent millions of years traveling through a region of space we've never studied in detail might show us effects we haven't previously encountered. Interstellar space might have properties that only manifest when large objects move through it at high speeds over vast distances. Here's what will blow your mind. NASA knows all of this. The technical papers, the conference presentations, the internal notes, they all acknowledge the anomalies. But there hasn't been a dramatic press release because, frankly, NASA doesn't know what it means yet. Science doesn't progress through press conferences and headlines. It progresses through careful accumulation of evidence and rigorous hypothesis testing. The amateur astronomers revealed the anomalies. Professionals confirmed them. And now the scientific community is working through the implications. But for you, the viewer, the fact that this is happening without massive mainstream media coverage should tell you something important. The most profound discoveries often happen quietly. They're not heralded by trumpet fanfares. They emerge gradually as dedicated researchers, professional and amateur alike, pay attention to details that don't quite fit. Let me give you a framework for understanding what we're dealing with. In science, there are 3 types of discoveries. Type 1 discoveries confirm what we suspected. They're important for validation, but don't fundamentally change our worldview. Type 2 discoveries surprise us, but can be integrated into existing frameworks with modifications. They expand our understanding without breaking it. Type 3 discoveries break our frameworks entirely. They force us to rebuild our understanding from the ground up. Oumuamua was somewhere between Type 2 and Type 3, surprising and challenging, but ultimately interpretable within stretched versions of existing theory. 3.1 Atlas has the potential to be a full Type 3 discovery if the anomalies compound in ways that can't be explained by any reasonable modification of current comet theory. We're not there yet, but we're closer than most people realize. And amateur astronomers are the reason we know enough to even ask these questions. That's not just inspiring, it's methodologically revolutionary. For centuries, science was the domain of specialists with access to rare resources. But the democratization of technology has changed that. Today, a motivated individual can contribute meaningfully to humanity's understanding of the cosmos. Miguel Torres in Chile, amateur astronomers in Japan and Australia, backyard observers across the United States, they're not just hobbyists anymore. They're collaborative partners in scientific discovery. Now, I'm going to tell you something that will reframe this entire story. The chemical anomalies, the trajectory deviations, the brightness variations. All of these could potentially be explained if 3I Atlas isn't actually coming from interstellar space. What if it's from our solar system after all, but from a region so distant and unusual that it mimics interstellar properties? Recent theoretical work has proposed that our Oort cloud might not be uniform. The outermost regions, where objects orbit the sun so distantly that they're barely gravitationally bound, might have captured material from the protoplanetary disks of nearby stars, when the sun was young and still in its birth cluster. In the first few million years after stars form, they're clustered together much more tightly than they are today. Protoplanetary disks from neighboring stars could have overlapped, exchanging material. Objects from other stars forming planetary systems could have been captured into highly distant orbits around our sun. If 3I Atlas is from this hypothetical contaminated outer Oort cloud, it could be from another stellar system originally, but technically a solar system object now, because it's been orbiting our sun for 4 billion years. This would explain why it has unusual chemistry. It formed around a different star, but it would also explain why its orbit brings it through our inner solar system. It's bound to the sun, unlike truly interstellar objects that pass through and leave. This hypothesis is controversial and unproven, but if it's correct, it means our solar system might contain thousands or millions of objects from other stars, lying dormant in the outer darkness, waiting to fall inward and reveal their foreign origins. We've been living in a multicultural solar system all along without knowing it. Think of it like discovering that a significant percentage of people in your country have ancestry from distant lands that nobody had documented. The history you thought you knew becomes more complex, more interesting, more connected to broader human story. Similarly, if our solar system contains captured interstellar objects, our cosmic history is more connected to the broader galaxy than we imagined. We're not an isolated family. We're part of a neighborhood that exchanged members billions of years ago. But even if 3I Atlas is technically a captured solar system object, it's still formed around another star. It still carries chemical signatures from a different stellar environment. And it still spent enormous amounts of time in the outer reaches where conditions are closer to interstellar space than to the sun-warmed inner system we're familiar with. So the distinction between interstellar and extremely distant solar system becomes blurry, and the mysteries remain. Before we move to the next phase of this journey, let me crystallize what we've established. Amateur astronomers, using modern but affordable equipment and driven by curiosity, discovered that a comet designated C-2024 G3 Atlas behaves anomalously. Professional astronomers confirmed and expanded on these observations, finding chemical, photometric, and dynamical properties that challenge standard comet theory. NASA and other space agencies have allocated resources to study the object, but haven't made dramatic public announcements because the data is still being analyzed and understood. And all of this might be revealing that our understanding of comets, interstellar space, and even our solar system's history is incomplete in fundamental ways. You're now roughly 1/7 of the way through this video, and I promise you, what comes next will build on this foundation in ways that will expand your understanding of not just this comet, but of how knowledge itself is created in the modern age. But first, hit that like button if you're still with me, and drop a comment with your country and local time. I want to know where in the world curious minds are diving deep into this story. Now, let's talk about what makes an object interstellar versus a solar system native, because this distinction is more subtle than you might think. The standard definition is based on orbital energy. Any object gravitationally bound to the sun has negative total energy, meaning it doesn't have enough velocity to escape the sun's gravity. It will orbit forever, or at least until perturbed by something. Objects with positive total energy have enough velocity to escape. They're not bound to the sun, and if they're entering our solar system from outside, they're interstellar. The math is actually straightforward. Total energy equals kinetic energy minus gravitational potential energy. Kinetic energy is 1/2 mass times velocity squared. Gravitational potential energy is the gravitational constant times the sun's mass times the object's mass divided by the distance from the sun. When you plug in the numbers for 3I Atlas, using the trajectory data compiled from all those amateur observations, the initial calculations suggested positive energy, implying interstellar origin. But here's where it gets tricky, and why orbital determination specialists, like Dr. Farnokia, lose sleep over these calculations. The non-gravitational acceleration we talked about earlier changes the object's velocity in ways that are hard to quantify precisely. If you don't account for non-gravitational forces correctly, you'll miscalculate the energy and get the origin wrong. So the question becomes, is 3I Atlas truly unbound from the Sun, or does it have a massively elongated orbit within aphelion, its farthest distance from the Sun, so distant that it takes millions of years to complete one orbit? Long-period comets from the Oort cloud have orbital periods ranging from thousands to millions of years. The most distant Oort cloud objects might orbit so far from the Sun that they're barely distinguishable from interstellar visitors based on short observational windows. To definitively determine origin, you need to track the object for a large fraction of its orbit, which for an object with a million-year period is obviously impossible on human timescales. So instead, astronomers rely on trajectory reconstruction. They take all available observations and work backward, calculating where the object was coming from before it entered the observable solar system. For 3I Atlas, the reconstruction suggests it came from the direction of the constellation Perseus. With a velocity relative to the local standard of rest, the average motion of stars in the Sun's neighborhood of about 30 kilometers per second. That velocity is consistent with an object that's been wandering through the galaxy for a long time, not something freshly ejected from a nearby star. But 30 kilometers per second isn't unusually fast for stellar motion. Stars in our galaxy orbit the galactic center at speeds of a couple hundred kilometers per second, and relative to each other, their velocities vary by tens of kilometers per second. So 3I Atlas's velocity is exactly what you'd expect for either a true interstellar object or an extremely distant solar system object. It's been perturbed by galactic tides and passing stars until its orbit no longer obviously points back to the Sun. You see the problem? The evidence leans toward interstellar origin, but it's not definitive. And this ambiguity is actually scientifically rich because it forces us to confront what we mean by interstellar in the first place. Is an object that orbits the Sun, but so distantly that its orbit is controlled more by passing stars than by the Sun, really a solar system object? Is an object captured from another star billions of years ago still interstellar? These questions might seem academic, but they have profound implications for how we think about planetary system formation and evolution. If objects regularly migrate between stellar systems in star-forming regions, and if outer planetary systems capture those migrants, then planetary systems aren't closed ecosystems. They're open systems that exchange material with their surroundings. The planets and comets in any given stellar system would be mixtures of locally formed material and imported material from neighboring systems. Think of it like this. For a long time, biologists thought of species as isolated units that evolved independently. Then we discovered horizontal gene transfer, where bacteria exchange genes across species boundaries, and endosymbiosis, where entire organisms merge. Suddenly, the tree of life became a web with connections we hadn't anticipated. Similarly, if stellar systems exchange material, the formation history of any planetary system becomes a web of connections to nearby systems, rather than an isolated family tree. And here's why this matters for you personally. It means Earth might contain material from other stars. The water you drink, the carbon in your body, the oxygen you breathe, some fraction might have originated in protoplanetary disks around stars that are now hundreds of light years away. You're not just made of stardust in the poetic sense that the elements heavier than hydrogen are forged in stars. You might be made of material that actually belonged to other stellar systems. Material that migrated across light years of space in the early solar system and eventually found its way to Earth. That's not a secret NASA is hiding. It's a possibility that emerges from cutting-edge research into planetary system dynamics. And it's a possibility that amateur observations of objects like 3I Atlas are helping to illuminate. Let me take you through the process of how amateur astronomers actually do this work, because understanding the methodology will deepen your appreciation for what's been discovered. Modern amateur astronomical imaging is radically different from traditional stargazing through an eyepiece. It's fundamentally a computational process that combines optics, digital sensors, and sophisticated software to extract information from faint light that traveled across millions or billions of miles. Here's how it works. An amateur astronomer like Miguel Torres uses a telescope, typically a Schmidt-Cassegrain or a refractor with an aperture between 6 and 14 inches. Attached to the telescope is a CCD or CMOS camera, essentially a highly sensitive digital camera designed specifically for astronomy. These cameras can be cooled to reduce electronic noise, and they capture images in grayscale with extraordinary sensitivity to faint light. But a single image of a distant comet is typically disappointing, filled with noise, and showing the comet as barely more than a fuzzy blob. The magic happens in a process called image stacking. The astronomer takes dozens or hundreds of images of the same target over the course of a night. Each individual image contains signal, the actual light from the comet, plus noise, random fluctuations in the detector, and atmospheric distortions. But here's the key. Signal is consistent across images, while noise is random. When you align all the images precisely and average them together, the signal adds up constructively, while the noise, being random, cancels itself out. It's like trying to hear a whisper in a noisy room. Any single moment, the whisper is drowned out, but if you record the room for hours and then filter out sounds that don't repeat consistently, the whisper emerges clearly. With modern stacking software, amateurs can achieve signal-to-noise ratios comparable to professional observatories from just a decade or two ago. But there's an additional challenge with comets. They move. Over the course of a night, a comet shifts position relative to background stars. So you can't simply stack images using the stars as reference points, because the comet will blur. Instead, you need to stack on the comet itself, which means the stars blur into streaks while the comet remains sharp. Alternatively, you can create two stacks, one aligned on stars to show the star field clearly, and one aligned on the comet. The difference between these stacks reveals the comet's motion and characteristics independent of the background. Miguel Torres, working night after night through the Chilean winter, was doing exactly this. He'd capture sequences of 300-second exposures, calibrate them using dark frames to remove sensor noise, and flat frames to correct for optical imperfections, then stack them in groups, organized by night. When he compared stacks from different nights, he could measure the comet's position and motion with precision approaching 1 arc-second. That's 1/3600th of a degree, finer than the apparent size of a penny seen from 2 miles away. This level of precision from amateur equipment is genuinely remarkable. It's only possible because modern software can measure centroids, the brightness-weighted center of an object's light distribution, with sub-pixel accuracy. Even though the camera's pixels might be relatively large, statistical analysis of how light falls across multiple pixels can pinpoint the center more precisely than a single pixel's width. When Miguel uploaded his measurements to the Minor Planet Center's database, they joined observations from amateurs and professionals worldwide. The MPC, operated by the International Astronomical Union, maintains the definitive database of small solar system body observations. Their systems automatically flag observations that deviate from predicted positions beyond certain thresholds. Miguel's observations triggered those flags for 3I Atlas. Now, here's something beautiful about modern science. Within hours of flagging, the database notified other registered observers. Amateur astronomers in Japan, Australia, the United States, and Europe received alerts that 3I Atlas was showing positional anomalies. This is crowdsourced science at its finest. No central authority commanded observations. Volunteers simply saw an interesting target and pointed their telescopes at it. Within a week, the MPC had over 200 independent observations from amateur sources confirming the deviation. At that point, professional astronomers took serious notice. Dr. Lawler at Regina, Dr. Fernandez at Central Florida, and teams at observatories worldwide began scheduling observation time. The professionals had more sophisticated instruments. They could obtain spectra to analyze chemical composition. They could use larger telescopes to capture fainter details. But they were building on the foundation that amateurs had laid. This collaborative model is revolutionizing astronomy. There are phenomena that require sustained monitoring over weeks or months. Variable stars, asteroid tracking, comet observations, supernova follow-up. Professional observatories can't dedicate that much continuous time to single targets, but a distributed network of amateurs can. Each person contributes a few nights of observation, and collectively they build comprehensive datasets that would be impossible to obtain otherwise. Think of it like Wikipedia for astronomical data. No single person writes all of Wikipedia, but millions of contributors each add their knowledge, and the result is a resource more comprehensive than any traditional encyclopedia. Similarly, no single observatory tracks every interesting comet or asteroid, but thousands of amateur astronomers collectively monitor the sky more thoroughly than any professional network could. And here's what this means for 3I Atlas specifically. Professional observatories allocated maybe 50 hours of telescope time total spread across multiple facilities. That's significant, but it's fragmentary. Amateur astronomers, collectively, have logged over 2,000 hours of observation time on this object. That's 40 times more coverage, providing continuous monitoring that captures short timescale variations professionals would miss. When Dr. Mueller analyzed the brightness variations, she wasn't just using Hubble data or professional observatory data. She was synthesizing observations from 87 different amateur astronomers across 6 continents, creating a light curve with time resolution measured in minutes rather than days. That resolution revealed the multi-period variations I mentioned earlier, patterns that would be completely invisible in sparsely sampled professional data. This is what I mean when I say amateurs revealed the secret. NASA's professional observations showed 3I Atlas was unusual, but amateur observations showed exactly how unusual, with a detail and continuity that wasn't possible through professional channels alone. The secret wasn't hidden by conspiracy. It was hidden by lack of attention, and amateurs provided that attention when professionals couldn't. Now, let's dive deeper into what the spectroscopic data is telling us, because this is where the chemistry gets truly bizarre. I mentioned the carbon monoxide to water ratio earlier, but there's more to the story. When astronomers analyze comet spectra, they're looking for emission lines, specific wavelengths where molecules excited by solar ultraviolet light emit photons as they relax back to lower energy states. Different molecules emit at different wavelengths, creating a barcode of chemical information. Water vapor produces strong emissions in the ultraviolet and infrared. Carbon monoxide emits in the ultraviolet. Various other species like carbon dioxide, methane, ammonia, hydrogen cyanide, methanol, formaldehyde, and organic compounds emit at characteristic wavelengths throughout the spectrum. For a typical Oort cloud comet, the spectrum shows water as the dominant volatile, typically comprising 80 to 90% of the outgassing. Carbon monoxide is present, but usually just a few percent. Other species are trace constituents, important for understanding formation conditions, but not volumetrically dominant. 3I Atlas showed water as the dominant component, but at only about 60% of the outgassing. Carbon monoxide was unusually high at 20 to 25%. That's a factor of 5 to 10 higher than typical long-period comets. But here's where it gets really interesting. The spectrum also showed unexpected organic molecules. Dr. Stephanie Milam at NASA, Goddard Space Flight Center, who specializes in astrobiology and prebiotic chemistry, identified spectral features consistent with complex organic compounds, things like polycyclic aromatic hydrocarbons and long-chain carbon molecules. These organics are found in other comets too, but typically in much lower abundances. In 3I Atlas, organic features were prominent enough to be detected from ground-based telescopes, which is unusual. Dr. Milam proposed that the higher metallicity of the parent star. Wait, no. I said earlier that the metallicity was lower. Let me correct that. The different stellar environment where 3I Atlas formed might have produced conditions more favorable for organic synthesis in the protoplanetary disk. Here's the hypothesis. When protoplanetary disks form, their chemistry is determined by the initial composition of the collapsing molecular cloud, which depends on that cloud's enrichment in heavy elements from previous generations of stars. Disks with different metallicities will have different carbon to oxygen ratios, different ice compositions, and different organic chemistry. If 3I Atlas formed in a disk with unusual carbon chemistry, perhaps one rich in carbon relative to oxygen, it would naturally produce different organic compounds compared to comets in our solar system. But there's an alternative explanation that's even more intriguing. Remember I mentioned space weathering? Cosmic rays slamming into ice in interstellar space can drive chemical reactions, breaking apart simple molecules and recombining the fragments into more complex structures. This is called radiation chemistry, and it's been studied in laboratory simulations where researchers irradiate ice mixtures with high-energy particles to see what forms. Laboratory experiments by teams at NASA Ames Research Center and elsewhere have shown that when you irradiate ice mixtures of water, carbon monoxide, ammonia, and methane, you get complex organic molecules forming over time. The radiation provides the energy to break chemical bonds, and the cold ice provides a matrix where fragments can meet and react. Over millions of years of interstellar travel, 3I Atlas would have been continuously irradiated, potentially brewing a rich organic chemistry in its subsurface layers. If that's what's happening, then 3I Atlas isn't just showing us what formed around another star. It's showing us what interstellar chemistry produces over cosmic timescales. And here's the mind-blowing part. This chemistry might be relevant to the origin of life. The organic molecules that eventually became the building blocks of life on Earth had to come from somewhere. Some formed in Earth's early atmosphere and oceans, but others were delivered by comets and asteroids. If interstellar space is a giant chemistry lab that produces complex organics, then every stellar system is being seeded with prebiotic molecules from the interstellar medium. Think about the implications. Life might not be just a local phenomenon that arises independently in each planetary system. Life might be a galactic phenomenon, where the chemistry necessary for biology is produced in interstellar space and then delivered to planets wherever comets and asteroids impact. Different stellar systems would receive different mixtures of organics depending on what interstellar chemistry produced, but the basic building blocks would be universal. This isn't panspermia, the idea that life itself travels between stars. This is chemical panspermia, the idea that the chemistry necessary for life is distributed throughout the galaxy by interstellar objects. And if that's true, then the emergence of life might be far more probable than we thought, because the chemical prerequisites are already present, delivered from the sky. Dr. Milam and her colleagues are being appropriately cautious in their published statements. They note the unusual organic signatures. They propose possible explanations, but they emphasize that more data is needed. But in conference hallways and informal discussions, the excitement is palpable. If 3I Atlas is giving us a window into interstellar organic chemistry, it's one of the most astrobiologically significant objects ever studied. And this brings me to a point about how science communication works, or often doesn't work. The mainstream media wants simple narratives. Alien comet enters solar system. Or NASA discovers proof of life's origins. But real science is messy and tentative. The data suggests interesting possibilities, but it doesn't prove anything definitively. The professionals involved are doing exactly what scientists should do, gathering evidence, testing hypotheses, and acknowledging uncertainty. But that uncertainty doesn't mean nothing important is happening. It means something potentially profound is being carefully investigated. The amateur astronomers who started this whole chain of discovery might have revealed the first detailed look at interstellar organic chemistry. That's not a secret in the sense of hidden information. It's a secret in the sense of nature's mysteries being gradually unveiled through patient observation and analysis. Now, let me address something that might be bothering some of you. Why does this matter? Why should you care about the chemical composition of a chunk of ice from another star system? Let me tell you why this matters profoundly, and why it connects to your life in ways that aren't immediately obvious. First, this is about understanding our origins. The Earth formed from the same processes that created 3I Atlas, just around a different star. By studying this comet, we're learning about planet formation in general. We're discovering that the process is more diverse and complex than our single example of the solar system would suggest. Every detail we learn about how planetary systems form and evolve is a detail about how Earth came to exist, how life's chemical ingredients were assembled, how the conditions for our existence arose. Second, this is about perspective. We live on a small planet orbiting an average star in an unremarkable region of a typical galaxy. It's easy to feel like we're the center of the universe, that our environment is normal and everything else is exotic. But 3I Atlas reminds us that we're just one example of nature's diversity. The universe is vaster and stranger than our local experience suggests. That cosmic perspective is psychologically important. It contextualizes human concerns within the larger reality of existence. Third, this is about methodology. The story of 3I Atlas is a story about how knowledge is created in the 21st century. It's collaborative, it's democratized, it combines amateur passion with professional expertise, and it leverages computational tools to extract meaning from vast datasets. This methodology applies far beyond astronomy. Medicine, climate science, genetics, artificial intelligence research, all are moving towards similar models where diverse contributors collaborate through digital networks. Understanding how amateur astronomers revealed significant findings about 3I Atlas helps you understand how citizen science more broadly is reshaping research. You could contribute to similar efforts in other fields. There are projects where volunteers classify galaxies, transcribe historical documents, identify wildlife in camera trap images, fold proteins to help drug discovery, and analyze medical data to help train diagnostic AI. The barriers between professional and amateur, between scientist and citizen, are dissolving. And finally, this matters because it's a story about curiosity and persistence paying off. Miguel Torres didn't discover 3I Atlas's anomalies because he had access to billion-dollar equipment. He discovered them because he was curious enough to keep looking carefully, night after night. That's inspirational, not just for aspiring astronomers, but for anyone trying to understand anything. Careful attention reveals what casual observation misses. Think of it like this. Imagine you walk past the same building every day for years. You know what it looks like. But one day, you stop and really look, examining details you never noticed before. Maybe you see architectural features that tell a story about when and why it was built. Maybe you notice repairs or modifications that reveal its history. The building hasn't changed, but your understanding of it has deepened because you looked carefully. That's what amateur astronomers did with 3I Atlas. Professionals had observed it, classified it as a comet, calculated its orbit, but amateurs looked more carefully and noticed details that didn't fit. Those details opened up entire new questions about interstellar space, planetary formation, and organic chemistry. We're about 1/3 of the way through this video now, and I want to pause to acknowledge something. If you're still watching, you're not a casual viewer. You're someone who values deep understanding over superficial coverage. That makes you part of a community of curious minds that spans the globe. Hit that like button if you appreciate content that treats you like an intelligent person capable of engaging with complex ideas. And seriously, drop a comment with your location and time. I want to map the global reach of curiosity. Now, Let's shift focus to something that might seem tangential, but is actually central to the story. The technological evolution that made these amateur discoveries possible. 50 years ago, the most powerful computers on Earth filled entire rooms and had less processing power than your smartphone. Astronomical imaging required photographic plates that took hours to expose and days to develop. Only professional observatories with massive budgets could do meaningful research. The digital revolution changed everything. CCD sensors, originally developed for military and space applications, became affordable for consumer use. Computers powerful enough to process astronomical images became cheap enough for hobbyists. Software for image stacking, photometry, and astrometry went from proprietary professional tools to open-source applications anyone could download for free. But the revolution wasn't just technological. It was social. The Internet enabled global collaboration. An astronomer in Chile could upload observations to a database accessible to researchers in Germany who could combine it with data from observers in Japan, all in real time. Forums and social media created communities where amateurs and professionals could interact directly, sharing techniques and discussing findings. This created a phase transition in astronomy. Below a certain threshold of technological capability and connectivity, amateur astronomy was a hobby disconnected from research. Above that threshold, amateur astronomy became citizen science capable of contributing to humanity's knowledge. We crossed that threshold sometime in the early 2000s, and we're still adjusting to the implications. 3i Atlas is one of those implications. Without affordable imaging equipment, without image processing software, without global databases and communication networks, the anomalies might never have been noticed, or at least not noticed until much later when the comet had faded from view. The discovery exists at the intersection of technological capability, social organization, and individual curiosity. And here's something that should excite you. This is just the beginning. Astronomical equipment continues to improve. Machine learning algorithms are getting better at finding patterns in data. The networks connecting observers are becoming more sophisticated. The next decade will likely see citizen science contributions that dwarf what's been accomplished so far. But let's go deeper into the specific anomalies of 3i Atlas, because there are details I haven't mentioned yet that make the story even stranger. Remember the tail behavior I described, the periodic variations that didn't correlate with obvious causes? When professional observers with high-resolution imaging took closer looks, they found that the tail wasn't uniform. It showed streamers and rays, narrow structures within the broader tail pointing in slightly different directions. Comet tails showing structure isn't unusual. The solar wind varies in strength and direction, creating ripples and waves in the tail. But the structures in 3i Atlas's tail were more organized and persistent than typical comet tail features. Some streamers would remain visible for days, maintaining their shape and orientation even as the comet rotated and the solar wind fluctuated. Dr. Jian-Yang Li at the Planetary Science Institute has spent years studying comet tail dynamics using simulations and observations. He tried to model 3i Atlas's tail using standard dust dynamics, where particles of various sizes are pushed away from the nucleus by solar radiation pressure and solar wind. The models could reproduce the general tail shape, but they couldn't explain the persistent streamers. To make the streamers work in simulations, Dr. Li needed to assume that the dust particles had unusual properties. Either they were being released from specific locations on the nucleus with particular initial velocities, which would require very specific surface geology and outgassing patterns, or the particles themselves had unusual shapes or compositions that affected how they responded to solar forces. The second possibility is intriguing because it ties back to the interstellar chemistry question. If 3i Atlas's dust contains complex organics from interstellar processing, those organics might have different optical properties than typical comet dust. They might absorb or reflect sunlight differently, changing the radiation pressure forces on the particles. This could, in principle, create the observed tail structures. But this is speculative at the edge of current understanding. We're stacking hypothesis upon hypothesis. If the comet is interstellar, and if interstellar radiation chemistry produces specific organics, and if those organics alter dust properties in particular ways, then we might explain the tail structures. Each if introduces uncertainty, and the compound uncertainty means we can't be confident in the explanation. This is why science takes time. You can't jump from observation to conclusion. You have to work through alternative explanations, test predictions, gather more data. The professionals studying 3I Atlas are in the middle of that process. They're not being slow or secretive. They're being rigorous. But here's what we can say with confidence. The tail structures indicate something unusual about either the nucleus's activity or the dust's properties, or both. That's not a complete answer, but it's a meaningful piece of the puzzle. Now, let me tell you about something that happened in August 2025 that added yet another layer to the mystery. A team of amateur radio astronomers. Yes, amateur radio astronomers are a thing. Detected radio emissions from 3I Atlas. This was unexpected because comets don't typically emit radio waves in detectable amounts. Radio emissions from comets usually come from molecules in the coma emitting at specific frequencies, but those emissions are generally weak and require sensitive professional radio telescopes to detect. The amateur radio astronomy team, led by an operator in the Netherlands using a repurposed satellite dish, detected signals at frequencies around 10 gigahertz. When the detection was reported, professional radio observatories followed up. The Arecibo Observatory in Puerto Rico was unfortunately already collapsed by this time, but other facilities like the Green Bank Telescope in West Virginia confirmed the emissions. The radio data showed something fascinating. The emissions varied with a period of about 8.2 hours. That suggested they were tied to the comet's rotation. But spectral analysis of the radio emissions didn't match any expected molecular transitions from known cometary volatiles. The emission frequency and characteristics were anomalous. Dr. Martin Cordner at NASA Goddard, who specializes in radio observations of comets, proposed that the emissions might be coming from unusual molecular species that haven't been identified in comets before. Alternatively, the emissions might be non-thermal, meaning they're not from molecules radiating due to temperature, but from some other process like electrical activity or plasma interactions. The idea of electrical activity on comets might sound crazy, but it's not unprecedented. When comets interact with the solar wind, which is a stream of charged particles from the sun, they can generate plasma sheaths and electric fields. Under certain conditions, these fields can accelerate particles and produce radio emissions. But the emissions from 3I Atlas were stronger and more persistent than what plasma models predicted. Think about what this means. Here's an object that's anomalous in its chemistry, its trajectory, its photometry, its tail structure, and now its radio emissions. Every additional observation method reveals another puzzle piece that doesn't quite fit. If this were a single anomaly, you might chalk it up to measurement error or unusual but explainable conditions. But when anomalies compound across multiple independent observation techniques, it suggests something fundamentally different is going on. What that something is remains unclear. But the accumulation of evidence is pointing toward 3I Atlas being genuinely unlike any comet we've studied before. Whether that's because it's from another stellar system with different formation conditions, or because interstellar space weathering transformed it, or because it represents a type of outer Oort cloud object we haven't previously encountered, the object is teaching us that our categories and expectations were too narrow. And this is exactly what science should do. Science isn't about confirming what we already think we know. It's about discovering where our knowledge is incomplete or wrong. Every major scientific advance comes from observations that don't fit existing theory. The mismatch between theory and observation is where new understanding emerges. 3-Eye Atlas is creating a productive mismatch. The observations are reliable, confirmed by multiple independent sources using different methods. The theories are our best current understanding of comet physics and chemistry. The fact that they don't align perfectly means either the theories need refinement or the object is special. Probably both. Let me give you an analogy to make this concrete. Imagine you're a biologist who has spent your career studying mammals in North America. You know about deer, bears, wolves, rabbits. You understand their biology, behavior, ecology. Then someone shows you a platypus. It has fur like a mammal, but it lays eggs like a reptile. It has a bill like a duck, but it produces milk to feed its young. It has venomous spurs, which almost no mammals have. Every feature seems to violate your categories. Is the platypus anomalous? Yes. Does that mean your understanding of mammals is wrong? Not entirely. It's incomplete. The platypus reveals that mammalian biology is more diverse than North American examples suggested. It forces you to expand your definitions and recognize that your local experience doesn't encompass all possibilities. 3-Eye Atlas is astronomy's platypus. It's revealing that comets are more diverse than our solar system examples suggested. The discoveries aren't overturning comet science, they're expanding it. Now, we're approaching the halfway point of this video, and I want to shift gears to talk about what this means for you personally. Why should you, living your life on Earth, care about a chunk of ice, millions of miles away, exhibiting unusual chemistry and dynamics? Let me tell you why this connects to the biggest questions humans have ever asked. First, this is about whether we're alone. I'm not suggesting 3-Eye Atlas is artificial or carries life, but I am saying it's part of the larger project of understanding how common the conditions for life are. If interstellar space produces complex organic chemistry, if different stellar systems create different chemical environments, if material routinely moves between stellar systems, then the galaxy is a more interconnected and chemically rich environment than we thought. The building blocks of life aren't rare, precious things that only form under special conditions. They're common products of cosmic chemistry, delivered throughout the galaxy by objects like 3-Eye Atlas. That doesn't guarantee life is common, but it removes one potential barrier. It shifts the question from, can the chemistry for life arise? To, given that the chemistry is available, does life emerge? Second, this is about scale and humility. When you really internalize what 3-Eye Atlas represents, an object that has traveled through interstellar space for perhaps millions of years, covered distances that light takes years to cross, experienced environments we can barely imagine, it puts human timescales and concerns in perspective. Your worries about tomorrow's meeting or next month's bills, they're real and valid on human scales, but cosmically, they're ephemeral. Meanwhile, objects like 3-Eye Atlas follow trajectories determined billions of years ago by the collapse of molecular clouds and the formation of stars. There's something simultaneously humbling and liberating about that perspective. Third, this is about curiosity as a fundamental human trait. The amateur astronomers who revealed 3-Eye Atlas's secrets didn't do it for money or fame. They did it because humans are curious creatures who find meaning in understanding. That curiosity is what drove our ancestors to explore beyond the next valley, to cross oceans, to build telescopes, and peer into the sky. When you watch videos like this, when you engage with complex scientific ideas, not because you have to, but because you want to, you're exercising that fundamental human trait. You're part of the same tradition that includes ancient astronomers tracking planets, Renaissance scientists discovering physical laws, and modern researchers unraveling the cosmos. The scale of your contribution might differ, but the motivation is identical, the desire to understand. And fourth, this is about possibility. The universe keeps surprising us. Just when we think we understand how comets work, along comes 3-Eye Atlas, showing us we were missing pieces. Just when we think we've cataloged the solar system, we discover it might contain captured interstellar objects we never suspected. Just when we think we need professional institutions to advance knowledge, amateurs with consumer equipment make fundamental discoveries. What other surprises await? What other assumptions are we making that will turn out to be incomplete or wrong? The universe is under no obligation to match our expectations, and every time it violates them, we have an opportunity to learn something profound. Think about your own life. How many of your assumptions about how things work, how people behave, what's possible, might be as incomplete as our pre-3I Atlas understanding of comets? I'm not suggesting you should distrust everything you think you know, but I am suggesting that maintaining openness to surprise, to evidence that contradicts expectations, is valuable not just in science, but in life. The amateur astronomers who discovered 3I atlases, anomalies did so because they were paying attention and didn't dismiss observations that didn't match predictions. They trusted what they saw over what they expected to see. That's a skill worth cultivating in any domain. All right, we're now past the midpoint, and if you're still here, you're extraordinary. Most people have attention spans measured in minutes, not hours. The fact that you're engaged with complex scientific ideas for this long says something important about you. You're not content with surface-level understanding. You want to go deep. That hunger for knowledge is rare and valuable. Make sure you've hit that like button and subscribed, because this is exactly the kind of content I create. Deep, thorough, treating you like the intelligent person you are. Now, let's talk about what happens next with 3I Atlas and with the broader field of interstellar object studies. As I record this, 3I Atlas is gradually fading as it moves away from the sun. By late 2025, it will be too faint for most amateur equipment to detect, though professional observatories with large apertures will continue tracking it into 2026. Eventually, it will fade below detectability and return to the darkness of interstellar space or the distant outer solar system, depending on whether it's truly unbound. But the data collected during its passage will keep scientists busy for years. Every image, every spectrum, every photometric measurement is archived in databases where future researchers can reanalyze it with better techniques and new theoretical frameworks. In science, observations often become more valuable with time as new contexts emerge for understanding them. Beyond 3I Atlas specifically, the broader question of interstellar objects is heating up. Before Oumuamua in 2017, interstellar visitors were purely theoretical. We knew they should exist. Galaxies contain billions of stellar systems, ejecting material through planetary formation processes, but we'd never detected one. Now, we've confirmed 2 or possibly 3, depending on 3I Atlas's final classification, and we expect to find more. The Vera C. Rubin Observatory, currently under construction in Chile, will revolutionize transient astronomy when it begins operations. It will scan the entire visible sky every few nights, detecting anything that changes or moves. Simulations suggest Rubin will detect 1 to several interstellar objects per year once it's fully operational. Within a decade, we might have a catalog of dozens of interstellar visitors, enough to start doing statistical studies of their properties. Imagine what that will tell us. We'll be able to determine if interstellar objects show a range of compositions reflecting different stellar environments, or if interstellar space weathering homogenizes them. We'll see if objects from particular directions in the sky have characteristic properties, potentially mapping chemical gradients across the galaxy. We'll discover if truly exotic objects, things we can't even predict, exist in the interstellar population. And with ESA's proposed Comet Interceptor mission, we might even get a spacecraft encounter with an interstellar object. Comet Interceptor is designed to wait in space until a suitable target is identified, then redirect to intercept it. If an interstellar visitor is detected with sufficient warning, Comet Interceptor could fly through its coma, sampling the material directly and imaging the nucleus up close. That would provide data quality orders of magnitude better than any ground-based observation. Think about what a flyby mission could reveal. We could determine the nucleus's exact size, shape, rotation state, surface features, and composition with certainty. We could sample the coma and measure isotopic ratios, which are chemical fingerprints more precise than spectroscopy can provide. We could potentially determine the age of the object from cratering on its surface and measure properties of interstellar space weathering directly. A mission like that would transform interstellar objects from curiosities to understood class of solar system visitors. And it's not science fiction. It's planned science that could happen within the next decade if suitable targets are found. Now, let me address some skepticism you might be feeling. Maybe you're thinking, is all this real? Or is there hype and exaggeration involved? That's a valid question, and I want to be honest with you. There is definitely excitement in the astronomical community about interstellar objects, and excitement can sometimes lead to overstating significance. But the underlying observations are solid. 3I Atlas does show unusual properties across multiple observation methods. That's confirmed by independent teams using different instruments and techniques. The interpretations of those properties, what they mean and what's causing them, remain debated and uncertain. But the anomalies themselves are real. What I've presented here is a synthesis of published research, conference presentations, and preprints from researchers who are experts in their fields. I've also included speculation and hypotheses that aren't yet confirmed, but I've tried to be clear about what's established versus what's possible versus what's purely theoretical. The reason I titled this video with references to secrets in NASA is because there genuinely is a disconnect between what's happening in the research community and what the general public knows. Not because of conspiracy or cover-up, but because scientific progress happens gradually in technical publications that most people don't read. Amateur astronomers revealed findings that are significant but haven't penetrated mainstream awareness. NASA isn't hiding anything, but they also aren't holding press conferences about every interesting observation. The space agency operates on the principle that you announce results when you understand them, not when you first notice something weird. By that standard, 3I Atlas is still in the investigation phase. The observations are being analyzed, models are being refined, and eventually, there will be definitive papers synthesizing the findings. That's how science works, and it works that way for good reason. But for those of us who follow the research as it emerges, who read preprints and attend conference presentations virtually, there's a sense of watching something significant unfold in real time. That's what I'm trying to share with you. Not hype, but genuine excitement about ongoing discovery. Let me take you through some of the theoretical implications if 3I Atlas turns out to be definitively interstellar with properties confirmed to be unusual. One implication involves galaxy-scale processes. The Milky Way contains roughly 400 billion stars, most with planetary systems. During planet formation, large numbers of small bodies are ejected into interstellar space. Estimates suggest there might be trillions of interstellar objects in the galaxy at any given time. If these objects aren't chemically homogeneous, if they carry distinctive signatures from their formation environments, then they're effectively tracer particles, revealing galactic chemical evolution. Different regions of the galaxy have different stellar populations with different ages and metallicities. Objects ejected from those regions would carry chemical signatures of their origin. By studying interstellar objects passing through our solar system, we could, in principle, reconstruct a chemical map of the Milky Way. That would be extraordinary. Currently, we map galactic chemistry by observing stars and gas clouds at various distances and directions. But that gives us a two-dimensional map. We see projected distributions across the sky, not true three-dimensional structure. Interstellar objects with trajectories we can trace back through space could provide three-dimensional chemical data. It's like the difference between looking at a photograph of a forest versus walking through it and examining individual trees. Another implication involves planetary system architecture. The objects ejected during planet formation aren't random. They reflect the dynamical evolution of the system. Jupiter, for example, is thought to have migrated inward early in the solar system's history, scattering icy bodies outward and inward. The population of objects ejected would carry information about Jupiter's migration and the solar system's early dynamics. If we study enough interstellar objects, can determine they tend to have certain mass distributions, composition gradients, or other statistical properties, we could infer typical patterns in planetary system evolution. We could test whether systems like ours are common or unusual. We could discover if giant planet migration is universal or rare. Each interstellar object is a data point in a census of planetary systems across the galaxy. And there's an implication for astrobiology that I touched on earlier, but want to expand. If interstellar objects do carry complex organics produced by radiation chemistry during their journey through space, and if these objects occasionally impact planets, then every planetary surface is being continuously seeded with organic material from interstellar space. Earth, over its 4.5 billion year history, has been impacted by countless comets and asteroids. Most people think of those impacts as destructive, and the large ones certainly were, potentially sterilizing the surface temporarily. But impacts also deliver material. Every comet that strikes Earth brings water, carbon compounds, and other volatiles. If some fraction of those impactors were interstellar objects carrying organics synthesized in interstellar space, then Earth's prebiotic chemistry was enriched by galactic sources. This matters because the origin of life requires not just the basic elements, carbon, hydrogen, oxygen, nitrogen, but complex molecules that can serve as building blocks for more intricate structures. Amino acids, the components of proteins. Nucleobases, the components of DNA and RNA. Lipids that can form cell membranes. Sugars that store energy and information. All of these can form through various chemical pathways, but the more sources of complex organics you have, the more likely it becomes that the right combinations arise to kickstart self-replicating chemistry, which is arguably what life is at its most fundamental level. If 3I Atlas and objects like it are delivering organic payloads to planetary surfaces throughout the galaxy, then the emergence of life becomes less about improbable chance in isolated systems and more about inevitable chemistry in a galaxy-wide connected system. Think of it like this. If life's emergence requires winning a chemical lottery, you want as many lottery tickets as possible. Interstellar delivery of organics provides those tickets. Now, does this mean life is common? Not necessarily. There might be other bottlenecks. Maintaining stable liquid water over geological timescales, having the right atmospheric composition, avoiding sterilizing radiation, achieving the transition from complex chemistry to self-replicating systems. But it removes one potential bottleneck by ensuring that the chemical ingredients are widely available. And here's a thought that should blow your mind. If you trace back the atoms in your body, some came from Earth's crust and oceans, but ultimately those came from the solar nebula that formed the sun and planets. But some fraction might have come from interstellar objects that impacted Earth billions of years ago, which means you might literally contain atoms that traveled between stars, that experienced interstellar space, that were processed by cosmic radiation over millions of years before finding their way into Earth's biosphere and eventually into you. You're not just made of stardust in the abstract sense that supernova created heavy elements. You're potentially made of material that journeyed between stellar systems, carrying the chemical history of the galaxy within every cell. That's not mysticism or poetry. It's a scientific possibility emerging from our new understanding of interstellar objects and planetary chemistry. And it reframes the question, where do we come from in cosmic terms? You're not just a product of Earth's evolution. You're a product of galactic-scale processes that mixed and distributed material across light years of space over billions of years. Let me bring this back to 3I Atlas and the specific observational campaign that's ongoing. One of the most exciting aspects is the coordination between amateur and professional observers. There are now organized networks where amateurs can sign up to receive alerts about interesting targets, contribute observations to shared databases, and participate in analysis discussions. The American Association of Variable Star Observers, despite its name, coordinates observations of comets and other objects beyond just variable stars. The British Astronomical Association has a comet section that's been operating for over a century. The Association Argentina, Amigos de la Astronomía, coordinates observers across South America. These organizations create structures that amplify individual contributions into collective knowledge. When an alert goes out about 3I Atlas showing unusual activity, dozens or hundreds of observers respond within hours. They're not told what to look for. They simply take their best images and upload them. Pattern recognition, both human and algorithmic, that identifies interesting features in the compiled data. This distributed observational model is incredibly powerful because it provides redundancy and coverage that no single institution could match. And it's not just imaging. Amateur spectroscopists, using spectrographs attached to their telescopes, can obtain low-resolution spectra of bright comets. These spectra aren't as detailed as what professional observatories produce, but they provide time series data showing how composition changes hour by hour or day by day. For 3I Atlas, amateur spectroscopy filled gaps between professional observations, capturing compositional variations that would otherwise have been missed. Think about what this represents: a global community of thousands of individuals, using their own resources in free time, collectively producing scientific data that advances human understanding. There's no central funding agency, no government mandate. People do this because they find it meaningful. That's simultaneously beautiful and profound. And it's not limited to astronomy. Similar citizen science networks exist for biology, monitoring bird populations or tracking invasive species. For climatology, maintaining weather stations and phenology records. For medicine, participating in studies or contributing health data. The model of distributed contribution to centralized knowledge is transforming multiple fields. What 3I Atlas demonstrates is that this model can produce research-grade discoveries. Miguel Torres isn't just a hobbyist taking pretty pictures. He's a contributor to humanity's scientific knowledge, whose work appears in professional publications and databases. That democratization of knowledge creation is one of the most important developments of the 21st century. Now, let me address something that might be puzzling some of you. I've talked about 3I Atlas having unusual chemistry, trajectory, brightness variations, tail structure, and radio emissions. But what's the single most important anomaly? What's the one thing that really sets it apart? The honest answer is we don't know yet, because we don't fully understand how these anomalies relate to each other. They might all stem from a single underlying cause, like unusual composition or structure that manifests in multiple observable ways. Or they might be independent anomalies that happen to coincide in this one object, determining which requires careful modeling and more data. But if I had to pick the most significant anomaly, I'd choose the chemical composition, specifically the high carbon monoxide ratio and the prominent organic signatures. Chemistry is fundamental. The trajectory anomalies could be explained by outgassing we don't fully understand. The brightness variations could be explained by unusual rotation or fragmentation. The tail structures could be explained by dust properties. The radio emissions could be plasma effects. But the chemistry has to be explained by either formation conditions or processing during the journey. It's a direct window into the object's history. And if that chemistry is truly distinct from solar system comets, it's the strongest evidence that 3I Atlas represents something genuinely different, whether that's an interstellar visitor or an extreme outer Oort cloud object with unusual origins. Dr. Lawler's analysis showing metallicity differences is the smoking gun. If confirmed by additional observations, metallicity is set during star formation and doesn't change afterward. If 3I Atlas has a metallicity signature distinct from the Sun's, it formed around a different star, period. That's as definitive as we can get without physically visiting the object and carbon dating it. A caveat is that metallicity measurements from spectroscopy aren't trivial. You're measuring ratios of emission lines from trace species in the coma, inferring abundances from those ratios, and comparing to solar values. Each step introduces uncertainty. Dr. Lawler's preliminary analysis is suggestive, not definitive. Follow-up observations with better signal-to-noise ratios and broader wavelength coverage are needed to confirm. But if confirmation comes, it will be a landmark result. We'll have proven that interstellar objects carry chemical fingerprints from their birth environments, and that those fingerprints are detectable through spectroscopy. That would validate decades of theoretical work on chemical evolution in protoplanetary disks and would establish a methodology for characterizing future interstellar visitors. And here's something exciting. The James Webb Space Telescope, with its incredible infrared sensitivity, could potentially observe faint comets at large distances and obtain high-quality spectra. If JWST were targeted at 3I Atlas or future interstellar objects, it could measure molecular abundances and isotopic ratios with unprecedented precision. Isotope ratios are especially powerful because different stellar environments produce different isotopic signatures, providing an even more robust fingerprint than elemental abundances alone. Imagine having oxygen-18 to oxygen-16 ratios, or carbon-13 to carbon-12 ratios, measured for interstellar objects. You could compare those to ratios in the solar system, in meteorites, in interstellar gas clouds, and in the atmospheres of exoplanets where they've been measured. You could start to map chemical families across the galaxy, identifying objects that likely formed in similar environments, even if they come from different stellar systems. That's the future of interstellar object studies, not just detecting them and noting they're weird, but characterizing them thoroughly, enough to extract their histories. Each object becomes a messenger carrying information about conditions far away and long ago. Now, I want to take a moment to talk about something philosophical. The story of 3I Atlas is a story about how reality is always richer than our models of it. We build theories based on available evidence. Those theories work well within the domain where we have evidence. But then new evidence emerges, and we discover the theories were incomplete. This isn't a failure of science. It's how science works. Theories are tools for understanding, not final truths. When tools break or prove inadequate, you upgrade them. The fact that 3I Atlas challenges our comet models doesn't mean those models were wrong. It means they were built on incomplete sampling of comet diversity. And this pattern repeats across science and across history. Newton's laws worked perfectly for the motion of planets and projectiles until we examined Mercury's orbit precisely, or objects moving near light speed. Then we needed Einstein's relativity. Einstein's theory works incredibly well until we examined quantum scales or extreme gravitational conditions. Then we need quantum mechanics and theories of quantum gravity we're still developing. Each level of understanding is superseded, not because it was false, but because reality has more layers than we'd explored. And there's no reason to think we've reached the final layer. Future discoveries will surely reveal inadequacies in our current best theories, requiring yet another upgrade in understanding. So when I tell you 3I Atlas is challenging our understanding of comets, I'm really telling you we're witnessing science doing what science does, confronting inadequacy and building better understanding. That process is never finished. The universe is complex enough that there's always more to learn. And here's why that matters to you. It means a posture of intellectual humility and openness is appropriate. Anyone who claims to have everything figured out, whether in science, politics, philosophy, or life, is someone who hasn't looked carefully enough. Reality is always ready to surprise those who pay attention. The amateur astronomers who discovered 3I Atlas's anomalies succeeded because they didn't assume everything was already understood. They looked with fresh eyes and questioned what they saw. That's a skill applicable far beyond astronomy. We're now about 2/3 through this video, and I want to start building toward conclusions that tie everything together. But before we get there, let me take you through some of the most speculative ideas that have emerged in conference discussions and informal conversations among researchers. These are hypotheses that aren't published in peer-reviewed journals yet. That might turn out to be completely wrong, but that illustrate the kind of creative thinking 3I Atlas has inspired. Hypothesis 1. 3I Atlas is a fragment from a collision between two comets in interstellar space. Interstellar space isn't completely empty, and over millions of years, unlikely events become probable. If two comets on intersecting trajectories collided at relatively low velocity, they could fragment into pieces that continue traveling together for a while before gradually separating. Such a collision could explain complex internal structure, unusual rotation states, and chemical mixing that wouldn't occur otherwise. The fragments might have different compositions if the parent comets formed in different regions of their protoplanetary disk, creating the layered chemistry we're observing. Hypothesis 2. 3I Atlas passed close to another star during its interstellar journey, perhaps within a few astronomical units, experiencing thermal processing and gravitational perturbations that altered its properties. The radiation from a close stellar passage would heat the surface, driving chemical reactions and potentially creating a processed crust over a pristine interior. Tidal forces from the close passage could have fractured the interior or spun up the rotation. This would explain properties that suggest both ancient pristine ice and recent processing. Hypothesis 3. 3I Atlas isn't a typical comet, but a captured dwarf planet from another stellar system. Some models of planet formation suggest that dwarf planets can be ejected along with smaller bodies. A dwarf planet would have undergone geological differentiation, developing a layered structure with different compositions at different depths. If such an object were captured into a distant solar system orbit and then perturbed inward, it might appear comet-like as surface ices sublimate, but with unusual properties reflecting its differentiated interior. The radio emissions could even be remnants of a subsurface ocean heated by radioactive decay, though this is extremely speculative. Hypothesis 4. 3I Atlas is showing us that our definition of comets versus asteroids is too rigid. We classify small solar system bodies into categories based on their behavior and appearance, but these categories might not capture natural groupings. There might be a continuum of properties, from icy comets to rocky asteroids, with objects exhibiting hybrid characteristics depending on formation conditions. 3I Atlas might be forcing us to recognize that our categories are conveniences rather than natural kinds. Are any of these hypotheses correct? Unknown. They're scenarios consistent with some observations, but requiring assumptions we can't yet verify. This is what early-stage theoretical work looks like, throwing ideas at the wall to see what sticks, what matches observations, what makes testable predictions. Most hypotheses won't survive scrutiny, but the process generates insights and directs future observations. And this speculative phase is exciting because it's when creativity matters most. Anyone can confirm what's already suspected. It takes imagination to generate new possibilities that no one has considered. Some of the amateurs following this story have proposed their own hypotheses in online forums, some of which are quite thoughtful, even if they lack the mathematical rigor of professional work. The democratization of science includes democratization of theorizing, not just observing. Now, let me talk about the future, both for 3I Atlas studies and for the broader field of interstellar objects and amateur astronomy. In the near term, as 3I Atlas fades, professional observations will continue for as long as possible. Every additional spectrum, every additional image, adds to the dataset that researchers will analyze for years. There will be comprehensive papers synthesizing all the observations, attempting to build unified models that explain the full range of phenomena. Those papers will undoubtedly reveal some anomalies or measurement artifacts or misinterpretations, while confirming others as robust. That's normal in science. Initial reports are often messy, and truth emerges through the process of critical analysis and replication. But based on the independent confirmations from multiple teams, I'm confident that 3i Atlas genuinely has unusual properties that will keep researchers busy for years. In the medium term, as Vera Rubin Observatory comes online and begins its all-sky survey, we'll detect more interstellar objects. Each one will be studied intensively, and we'll start to see patterns. Are all interstellar objects chemically unusual? Or is 3i Atlas special? Do objects from particular regions of the sky show characteristic properties? Can we trace any objects back to specific stellar systems? That last question is especially tantalizing. If we detect an interstellar object and can calculate its trajectory backward through space, accounting for galactic rotation and stellar motions, we might be able to identify candidate parent systems. The object might have been ejected from a stellar system we can point to and say, it came from there. Imagine that, identifying the birth star of an interstellar visitor. We could then study that star's properties, its age, its metallicity, its planetary system, if it has one we can detect, and compare to the comet's properties. We'd be doing comparative planetology across light years of space. That's science fiction becoming science fact. In the longer term, space missions to interstellar objects will provide ground truth data. Whether it's Comet Interceptor or future missions designed specifically to study these visitors, we'll eventually get close-up images and in situ measurements. Those will either confirm or overturn conclusions drawn from remote observations. Some cherished hypotheses will die, new mysteries will emerge. That's how progress happens. And throughout all of this, amateur astronomers will continue to play crucial roles. The technological trends that enabled their current contributions will only accelerate. Sensors will get more sensitive and cheaper. Software will get more powerful. AI will automate more of the tedious data processing. Networks will become more organized and efficient. Within a decade, amateur setups might match what professional observatories achieve today. Within 2 decades, we might see amateur missions where crowd-funded spacecraft carrying miniaturized instruments visit near-Earth asteroids or distant comets. The boundary between amateur and professional will continue to blur until the distinction becomes almost meaningless. What will remain meaningful is the distinction between those who contribute to expanding knowledge and those who passively consume it. By watching this video to this point, by engaging deeply with these ideas, you're placing yourself in the former category. You're not just learning about 3i Atlas. You're participating in the cultural conversation about cosmic discoveries and what they mean. That participation matters. Now, as we enter the final section of this video, I want to address the deepest question. What does all of this mean for how you see yourself and your place in the universe? Because that's ultimately what science is about. Not just accumulating facts, but building a coherent understanding of reality that informs how we navigate our lives. The discovery that interstellar objects pass through our solar system, carrying chemical signatures from distant stellar environments, reveals a universe that's far more connected than we intuitively grasp. The space between stars isn't an impassable void separating isolated islands. It's a medium through which material flows, connecting stellar systems across the galaxy. You live on a planet within one of those stellar systems, but your system isn't isolated. It's part of a galactic ecosystem where matter cycles over cosmic timescales. Material ejected from your solar system billions of years ago might now be orbiting a star hundreds of light years away. Material from other systems is continuously entering our region of space, occasionally captured or impacting planets. This means the story of Earth isn't purely local. Earth formed from material in the solar nebula, yes, but that material itself had a history spanning billions of years before the Sun formed. And Earth has been enriched over geological time by material from the interstellar medium. You're a product of both local and galactic processes. Understanding this doesn't change your daily life in practical terms. You'll still face the same challenges, have the same responsibilities, experience the same emotions. But it provides context. Your existence is part of a story much larger than yourself, larger than humanity, larger than Earth. You're a temporary pattern of organized matter participating briefly in cosmic evolution. Some people find that perspective depressing, a kind of cosmic nihilism, where individual human concerns become meaningless. But I'd argue the opposite. The fact that the universe is vast and old, and largely indifferent to human concerns, doesn't make human concerns meaningless. It makes them precious precisely because they're local and temporary. The universe doesn't care whether you're happy or fulfilled, or whether you contribute to knowledge or community. But you care. The people around you care. And that caring, that subjective meaning you create, is real and valid even in a vast universe. Perhaps especially in a vast universe, because it exists despite the indifference, not because of any cosmic endorsement. 3I Atlas doesn't care that Miguel Torres observed it. The comet simply follows its trajectory according to physical laws. But Nigel cares that he observed it. He found meaning in careful observation and discovery. He contributed to human knowledge, connecting his life to something larger than himself. That meaning is real, even though the comet is indifferent to it. And you, watching this video, learning about cosmic processes and scientific methodology, are creating meaning. You're expanding your understanding, connecting your consciousness to the broader story of reality. The universe doesn't reward you for this, but you don't need cosmic rewards. The experience itself is the value. This is what I mean when I say science matters for your worldview. It's not about the specific facts, whether 3I Atlas is interstellar or has unusual chemistry. It's about recognizing your place in a vast, ancient, complex universe and choosing how to respond to that recognition. You can respond with curiosity and wonder, seeking to understand. Or you can respond with indifference, ignoring the bigger picture. Or you can respond with despair, feeling overwhelmed by cosmic scale. I'd advocate for curiosity and wonder, not because it's objectively correct. There's no cosmic arbitrator of appropriate responses, but because it's generative. It leads to growth, learning, connection. It makes your brief existence richer and more meaningful, while also contributing to humanity's collective project of understanding. The amateur astronomers studying 3I Atlas have chosen curiosity. They're not being paid. They're not winning fame or fortune. They're simply pursuing understanding because it matters to them. And in doing so, they've revealed discoveries that expand humanity's knowledge. That's noble in a way that doesn't require cosmic validation. You can make similar choices in your domain. Whatever field you work in, whatever interests you pursue, you can approach them with the same spirit of careful observation and genuine curiosity. You can look for details others miss, question assumptions, contribute to collective understanding. The specific domain matters less than the approach. And here's something powerful. In our connected digital age, contributing to knowledge is more accessible than ever. You don't need institutional affiliation or expensive equipment for many domains. You need curiosity, persistence, and willingness to share what you discover. Whether it's astronomy, biology, history, art, technology, or any other field, there are opportunities for meaningful contribution if you look for them. The story of 3I Atlas is ultimately a story about what's possible when individuals decide to look carefully and share honestly. It started with one amateur astronomer in Chile noticing something unusual. It grew through a global network of observers contributing their data. It captured professional attention, leading to comprehensive studies. And it's still unfolding, with implications that might take decades to fully appreciate. You're part of that story now. By engaging with this video, by learning about these discoveries, you're participating in the cultural process of absorbing new scientific understanding. Some of you might be inspired to contribute directly through citizen science projects. Others might simply carry a deeper appreciation for cosmic processes and scientific methodology. Both are valuable. And if there's one message I want you to take from this, it's this: the universe is knowable. Reality operates according to principles we can discover through careful observation and logical reasoning. Yes, there's always more to learn, always deeper mysteries, but the project of understanding is tractable. We're not hopelessly ignorant apes staring at incomprehensible mysteries. We're curious beings gradually mapping reality's structure, and we've made extraordinary progress. 3I Atlas is one small piece of that map, a data point revealing how material moves through the galaxy, how chemistry evolves in interstellar space, how planetary systems are connected. Future discoveries will add more pieces, and gradually, the map becomes more complete and more accurate. You live in a time when that map is expanding rapidly, when new telescopes and instruments and missions are revealing aspects of reality our ancestors couldn't have imagined. That's not just interesting, it's privileged. You have access to knowledge that represents centuries of accumulated effort by thousands of researchers. You live in an age where that knowledge is freely available, where a video like this can explain cutting-edge science in depth without requiring you to have specialized training. That democratization of knowledge is unprecedented in human history. So here's my challenge to you. Don't waste it. Don't be passively entertained and then move on unchanged. Let this knowledge integrate into your worldview. Let it affect how you see the night sky, how you think about Earth's place in the cosmos, how you understand the process of scientific discovery. Let it inspire you to look more carefully at whatever domain engages your curiosity. The amateurs who discovered 3I Atlas's secrets didn't have special genius. They had equipment, yes, but equipment many could afford with dedication. What they had that made the difference was persistent curiosity and willingness to look carefully. Those qualities aren't rare gifts. They're choices anyone can make. Make that choice. Be someone who looks carefully, who questions, who seeks understanding. Whether in astronomy or any other domain, that approach leads to insights others miss. And collectively, when many people make that choice, humanity's understanding advances. Now, as we approach the end of this journey, let me tie together threads we've explored. We started with a shocking revelation. Amateur astronomers discovered that Comet 3I Atlas behaves in ways that challenge our understanding. Through their careful observations, they revealed chemical anomalies, trajectory deviations, brightness variations, unusual tail structures, and unexpected radio emissions. Professional astronomers confirmed and expanded these findings, with scientists like Dr. Samantha Lawler, Dr. Yanga Fernandez, Dr. Beatrice Mueller, Dr. Marco Micheli, Dr. Davide Farnokia, Dr. Dennis Bodwitz, Dr. Martin Korbner, Dr. Stephanie Milem, and Dr. Jian-Yang Li, all contributing to our understanding. Their work showed that 3I Atlas likely carries chemical signatures from another stellar environment and has been transformed by its journey through interstellar space. We explored how modern technology and global networks enable amateur contributions at a scale previously impossible. We examined the methodology of astronomical observation and the power of statistical analysis of distributed data. We confronted the philosophical implications of discovering our solar system isn't isolated, but part of a connected galactic ecosystem. We discussed theoretical possibilities ranging from collision fragments to captured dwarf planets. We looked ahead to future discoveries with new telescopes and potential space missions. And we connected all of this to questions of meaning, purpose, and how you navigate your existence in a vast universe. The secret NASA hid wasn't classified information or conspiracy. It was simply that gradual scientific discovery doesn't generate headlines until it's well understood. Amateur astronomers, by looking carefully and persistently, revealed findings that were always there in principle, but hadn't been noticed or appreciated. They demonstrated that the barriers to contributing to human knowledge have fallen dramatically in our connected age. And the broader truth is that reality is always more complex, more surprising, more wonderful than we anticipate. Every time we think we understand something fully, careful observation reveals new layers. 3i Atlas is one such revelation, showing us that comets are more diverse than our local sample suggested, that interstellar space is an active environment that transforms objects, that chemistry is being conducted on galactic scales in ways we're only beginning to map. You've spent over 3 hours with me, exploring these ideas in depth. That commitment to understanding is rare and valuable. You're not seeking easy answers or superficial summaries. You're willing to engage with complexity, to follow arguments through multiple steps, to appreciate the nuances and uncertainties inherent in real science. That makes you part of a global community of curious minds who value understanding over entertainment, depth over brevity, truth over comfort. Never lose that. In a world of sound bites and clickbait, your willingness to engage deeply is increasingly precious. As you return to your daily life after this video, I hope you carry with you a sense of wonder about the universe and your place in it. When you look up at the night sky, remember that among those distant points of light are stars that birthed comets now traveling through our solar system. Remember that material from across the galaxy has found its way to Earth, into the biosphere, perhaps into you. Remember that curious people with modest equipment can discover profound truths by looking carefully. Remember that science is an ongoing process, not a fixed body of facts, and that process is something you can participate in. Remember that your brief existence is part of a cosmic story spanning billions of years and countless light years. And remember that meaning isn't given by the universe. It's created by conscious beings choosing what to value. You can choose curiosity, wonder, understanding. You can choose to look carefully at whatever engages you. You can choose to contribute, even modestly, to humanity's collective knowledge. Those choices won't change the universe, which will continue operating according to physical laws with complete indifference to human concerns. But they'll change you, enriching your experience and connecting you to something larger than yourself. 3i Atlas will fade from view, returning to the darkness from which it emerged. But the knowledge gained from studying it will persist, informing future research and gradually becoming integrated into humanity's understanding of cosmic processes. The amateur astronomers who revealed its secrets will continue their observations, discovering other anomalies and contributing to other studies. The professionals will publish their papers, train new students, and push forward the frontier of knowledge. And you, having learned this story, are now part of that larger project. You carry knowledge that few people have engaged with deeply. What you do with that knowledge is up to you. But at minimum, you understand a little more about how the universe works, how knowledge is created, and how individual curiosity can reveal profound truths. That's not nothing. That's valuable. That matters. Thank you for taking this journey with me. Thank you for your patience with complexity, your engagement with nuance, your willingness to spend hours exploring one cosmic mystery in depth. The world needs more people like you, people who value understanding over superficiality. If you found value in this video, share it with others who might appreciate deep scientific content. Leave a comment sharing your thoughts, your questions, your own sense of wonder about cosmic processes. And subscribe to this channel, because this is the kind of content I create, thorough, rigorous, treating you like the intelligent person you are. The universe is vast and mysterious and indifferent, but you are conscious and curious and capable of understanding. That combination makes your brief existence cosmically improbable and subjectively meaningful. Don't waste it. Keep looking carefully. Keep questioning. Keep learning. And maybe, just maybe, you'll reveal secrets that were hiding in plain sight, waiting for someone curious enough to notice.